All right, so in this video, I want to get into a little bit of more, I just like behind the scenes when a reaction occurs, right? Giving us a better picture of like where the rate laws for a reaction actually come from, kind of how we can determine what pathway a reaction is going through when it goes from reactants into products. So the idea behind this is that a lot of reactions, while we may kind of simply show them as like a simple reactants turning into products, are not actually as simple as that, right? So for instance, we can consider this reaction here of nitrogen dioxide reacting with carbon monoxide to produce nitrogen monoxide and carbon dioxide. Now this reaction, while I have it written out as just this simple like reactants turning into products, it actually takes part in two steps. So initially you have your nitrogen dioxide reacting to form nitrogen trioxide and nitrogen monoxide. Then the nitrogen trioxide from that first reaction, that's what's going to react with the carbon monoxide to produce then new products of nitrogen dioxide and carbon dioxide. So right, if we look at these, two steps individually, we can see some similarities and some differences between them. The idea is that when we take these two steps and we kind of add them together, that equals our overall reaction. So this is kind of similar to, maybe what you saw in like the Hess's law type stuff from Chem 161 and 162. But right, in those examples, you maybe had multiple reactions being added together, and like the product from one reaction was maybe exactly the same as a reactant in another reaction. And so when you add those reactions together, you're essentially going to remove anything that's the same on both sides of the equation. So here, right, when I add together these two steps, things like the nitrogen dioxide, because it appears in both the reactants and the products, part of that is going to get canceled out, right? Or the nitrogen trioxide, well, it's a product in step one. In step two, it's a reactant, and so that effectively just disappears. That's why we don't see it in the overall equation at the top here. But what's really important to note about these different steps is because they are themselves different reactions, they're going to have different rates. And so in this case, actually, the first step of the reaction, that occurs rather slowly, whereas the second step can go very quickly on its own. But so right, this picture of the different steps that are going into our overall reaction, this is referred to as the reaction mechanism. This is essentially like the nitty-gritty of how a reaction occurs. It goes into very fine detail of what processes maybe behind the scenes are going on that make our overall reaction happen. Now, when we have a reaction mechanism, we're often going to see, again, like these kind of redundancies or things that appear both in the reactants and in the products. And specifically, if we have, say, some chemical that is produced in one step and then consumed in a later step, this is referred to as a reaction intermediate. So in this example, that nitrogen trioxide, right, because it comes from step one, but then it's used up in step two, that's why we don't see it in the overall reaction process, but it is itself part of the reaction. It's known as a reaction intermediate. Now, when we break apart our reaction into these mechanisms and we have those individual steps are referred to as elementary step, or also elementary reactions. Now, elementary here means like kind of simplified, right? Think of like elementary school as like baby school, right? Or like elements are like the most basic form of matter, right? An elementary reaction is kind of like the most simple reaction, which is to say that like any of these individual steps, they themselves are exactly as they appear, right? They don't have any other behind the scene. They're already in their simplest form, and so there's nothing kind of implicit or hidden about them. Now, what's really nice about that is that it makes actually studying the rate law for those individual reactions very simple, because the reaction order for every reactant in the rate law is just going to be equal to whatever the molar coefficient is in that balanced chemical equation. So for instance, if we look at this second reaction where we have 1 mole of nitrogen trioxide reacting with 1 mole of carbon monoxide, because those both have a molar coefficient of 1, each of those reactants is going to have a reaction order of just 1. But so that makes the rate law for that second reaction alone very simple, right? We would just say that the rate is equal to whatever the K constant is times the concentration of NO3 to the first power, and then times the concentration of CO also to the first power. So right, I have here the rate law for that second step. Again, because this is an elementary reaction, the molar coefficients just equal our reaction orders. Now again here, I want us to focus on the fact that, right, these two steps in the reaction have different rates themselves. So where reaction 2 goes very quickly, reaction 1 goes rather slowly. And so because of that, even though reaction 2 can happen very fast, it can only do that if it has reactants around, and those reactants, as we can see, come from reaction 1. So because that first step is very slow, right, it's actually going to kind of hinder the reaction from moving any more quickly, even though reaction 2 itself is technically fast. But so that slower reaction is going to kind of like bottleneck things, right? It's like keeping the chemicals in traffic so that they can't get to the next, say, very clear road, that next clear path. And so what that means then is that the rate law for the overall reaction is actually not dependent on the second step at all, right? The rate law for the overall equation at the top here is just defined as the rate equal to K constant times the concentration of nitrogen dioxide squared. So right, this rate law right here is technically the rate law of the first step. Because that first step is slow, it's going to decide what the rate is for the entire process overall. We refer to these slow steps as the rate determining or rate limiting steps, right? These are the elementary reactions that dictate and decide what the overall rate is of a reaction. So let's take a look at a potential energy diagram, not of that same reaction that we saw before, but a different multi-step reaction. So what I have right here is the potential energy diagram for the reaction of nitrogen monoxide and oxygen producing nitrogen dioxide. Now, as we can see at the bottom here, this is actually a two-step reaction mechanism. Again, we've got like this first reaction going on that produces first some nitrogen trioxide. Then that nitrogen trioxide, being an intermediate, is going to react to then form the final product, the nitrogen dioxide. Now, because this is, again, like a two-step reaction, we essentially have like two potential energy diagrams kind of crammed into one, right? If we look at the shape of this curve right here, you can see essentially like two hills, right? So before, when we were looking at our potential energy diagrams, we'd see just like a single hill with a single activation energy. Now we have these two steps happening, so each one is going to have its own activation energy and its own kind of hill shape to it. Now what that also means, right, is that for each one of these different steps in the reaction, they're going to have, you know, their own unique transition states, again, at that higher energy. But what's really important to note here is about just comparing like the relative activation energies of these two steps. We should see that the slower step, or the rate determining step in the mechanism, because it is so slow, right, we expect it to have a much higher activation energy associated with it. So we can see that in this diagram right here, right? In this case, the first step occurs quickly, the second step goes slowly. And so right in the potential energy diagram, we see a much larger hill for that second bump, right, rather than the relatively small first bump. But so again, if we have like a multi-step reaction like we see right here, each individual step is going to have its own activation energy, its own transition states. But what's really important to note there is that for the rate determining step, we expect it to have the highest activation energy, right, the greatest barrier to overcome. Now, lastly, in this chapter, I want us to take a look at kind of how we can maybe change activation energies by actually providing kind of an alternative mechanism or an alternative reaction pathway for any given reaction. So this is done through the work of catalysts. Catalysts are defined as chemicals that will speed up a reaction or increase the rate of a reaction, but a catalyst is kind of interesting because it's not actually necessarily like a reactant itself. It's present in the reaction mixture, but it doesn't actually get consumed throughout the reaction. So usually kind of how a catalyst will work is by just providing like an alternative pathway for our reactants to turn into products. So basically just giving a different mechanism for our reactant to product pipeline. So pictured right here is an example of a very common catalyst that you may have like in your car. This is a catalytic converter. So what this does is it takes nitrogen monoxide, which is a pretty noxious gas that comes from our exhaust, and that nitrogen monoxide is converted into nitrogen and oxygen alone. Now that reaction can occur naturally on its own, but it does like require kind of specific arrangements of the molecules of NO to kind of meet each other and align perfectly so that you do put the oxygens next to each other and the nitrogens next to each other. And when that happens on its own, right, the chances are fairly slim for that to actually occur. But if we supply this catalyst to the nitrogen monoxide, then it encourages the nitrogen monoxide to arrange in the proper formation to make that alignment occur, and so then that encourages the reaction to go by a little bit more quickly, right? Kind of just guides the molecules through the reaction a little bit more smoothly than if they were just doing it on their own. Now, how that looks energetically, right, we can kind of picture right here in a potential energy diagram. So I have in orange here, basically the potential energy of the uncatalyzed reaction, so without any catalyst around. And then in green is the catalyzed reaction. And so you can see that, right, these are going to have the same beginning and end result, but how they get from reactants to products just differs, right? When we have no catalyst around, we have like a very high activation energy, a very unstable transition state. But with the introduction of the catalyst, right, that provides an alternative pathway that is then going to have lower activation energies, so it's easier to overcome. Again, what's kind of interesting about the catalyst itself is that it's not consumed in the reaction at all. It may kind of act initially as a reactant, but it's also going to come out in the end as a product. So that's to say, like, the catalyst essentially gets recycled throughout the reaction. And so with just like a little bit of catalyst, you can make your reaction go fast for a long time, right? Because that catalyst does not get used up at all, it's not going to run out necessarily throughout the course of the reaction. Right, but so that's just how like reaction mechanisms and elementary steps and rate limiting steps work, as well as catalysis. Please let me know if you have any questions, and I'm always happy to help. Bye.